Hello everyone, in this video we would be discussing about joint probability. But before we proceed to joint probability, let us first review a couple of topics of importance to joint probability. So let us first review set operations. So for set operations, these three here are of vital importance for today's lecture. So namely, we have union, intersection, and then complement. So as per defined here, when we say union, union of two sets contains elements in both sets. When we say intersection, these are the similar elements found in both sets. And when we say complement, these are the elements here contains basically everything that is not included in the set. So as a review, let us have this for our example. So suppose that we have sets A, B, and C containing the following. So for set A, we have black, white, and gray as the colors. And then for set B, we have red, green, blue, pink. Then for set C, we have red, orange, yellow, green, blue, indigo, and then violet. So if we would be getting the union between A and B, and it can now be written as A, U, B. So this indicates that we are now to get the union between the two. What we will be doing is that we will be listing everything that is found in sets A and B. So with that, we will be writing black, white, gray, red, green, blue, and pink. So red, green, blue, and pink respectively. Okay, so that is basically union. So let us have another example. So what if we are now to get the union between B and C? So that what that means is that we will be listing everything found inside sets A and C. But take note here that since red here is similar, or let's say that red is found in both sets B and C, we will only write them once. So even though that this red here are found twice in B and C, we will only write them once because they are actually very similar already, or they are actually similar elements. So with that being said, guys, the union between B and C is red, green, blue, pink, orange, yellow, indigo, and then violet. So what we did once again was that we have just listed all of the elements here. And from that, guys, similar elements will only be written once. Okay, so proceeding. So with that being said, guys, for the intersection between B and C, when we say intersection, these are the similar elements found in the two sets. Meaning, so between B and C, the what you call this, the similar elements found here are the following. So we have red, we also have blue, and we also have green, I should say. So from that, guys, we will only write red, green, and blue. Okay, so that is for intersection. But what about for complement? When we say complement, once again, these are elements that contains everything that is not in the set. So in here, in our fourth example here, we would first get the union between A and C. So from that, guys, we will be writing everything found in A and C. So meaning that that is, again, this the union of A and C. So we have here black, we have here white, we have here gray, and the Roy G. Biv, or the red, orange, yellow, green, blue, violet, and then indigo. Okay, so we have all of these colors here. So that is the union between A and C. But what about for its complement? So its complement is what makes this set complete. So when we say complete set, we are now to talk about the complete sample space. So the only color here that is not included is the color pink. So from that, guys, the complement between the union of A and C is now just pink. Okay, so another great way to understand our topic is by visual representations. So using Venn diagram, so this is now the union between A and B. With that, guys, all of the elements of A and B are shaded. And when you are to get the intersection of both, then meaning that we will only get what is similar, or of course their intersection, and so on and so forth. So from that, let us proceed to our sample problem here, but then again, this is still a review from our past lecture. So this is still basic probability. Okay, so in this problem, in guessing a number from 1 to 10, what is the probability that the number or the guessed number is A, an odd number, B, a prime number, C, an odd prime number, D, an even prime number, and E, an odd number or a prime number? Okay, so this, once again, is still a review. We are not yet in joint probability, but once again, we will be getting there. Okay, so the first thing that I want to do here is by me making a Venn diagram as shown here. So suppose that this is the whole sample space, for example. So for example, this is the whole sample space. I will now represent the first circle here as A. And let's say that the second circle here is now B. Whereas A, let's say, is the odd number, for example, and B is now our primary number. Okay, so as per your early mathematics subjects, you know that odd numbers consist of the following but are not limited to. So we have 1, 3, 5, 7, 9, 11, and etc. And when we say prime numbers, so prime numbers are numbers whose only whole number factors is 1 and the number itself. So as for example, we have 1, we have 2, we have 3, we have 5, and we also have 7. But since we are only to guess a number from 1 to 10, or a whole number from 1 to 10, I will now list these numbers here in this Venn diagram. So for example, for number 1, is it an odd number, is it a primary number, or is it none of the above? So 1 as a number is both odd and primary. So meaning that I will be including them in the middle part here. So 1. But what about for 2? 2 is not an odd number, but of course it is still a primary number. So I will now include them here. So this is now number 2. But what about for 3? So number 3 is an odd number and it is also a prime number. So with that, guys, this is now 3. So it is both an odd number and a primary number. So what about for 4? So 4 is neither an odd number nor a primary number. So meaning that it will now be included here. So this is now number 4. So for number 5, it is both odd and primary. So what about for 6? 6 is also included here. So what about for 7? 7 is an odd number and also a primary number. But what about for 8? 8 is not or is neither an odd number nor a primary number. And for 9, the number 9 is an odd, it is an odd number, but it is not a primary number. Since 9 has factors of, in order for you to arrive at number 9, you would be multiplying 9 and 1, and also you can also multiply 3 and 3. So meaning since it has other factors other than the number itself and 1, and with that being said, that is 3 and 3, meaning that 9 is not a primary number any longer. And with that, we will now be putting them here for A. And once again, 10 is not a primary number, nor it is an odd number, so I will be including them here, 10. So, roll call. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Okay. So from that, guys, we will now be solving for the probability that the guessed number is an odd number. So once again, what happens here is that suppose that we are asked by a friend to guess a number from 1 to 10. Okay? So from that, we will now solve for the probability that we will be getting the correct answer if, let's say, the correct answer is an odd number. Okay? So, again, from our previous topic, that the probability of a certain event is equal to the number of events divided by the number of the sample space. And if we are now to talk about the sample space is now equal to, so how many numbers are here? So we have 10 numbers. Okay, so what about for the events? For the odd numbers, we will now count all of the numbers that is in set A. So meaning we have 1, 2, 3, 4, and then 5. So that is now your odd numbers. So without even writing the solution, just looking at the calculator to your left, our answer here, once again, is, so we have 5 possibilities. Once again, that is 1, 2, 3, 4, and 5. So 5 possibilities divided by the total sample space of 10. So that is now 0.5 or 50%. So that is now 0.5. So what about for prime numbers? So for prime numbers, if we would be counting them here. So we have, once again, 1, 2, 3, 4, and 5. Okay, so we have 5 prime numbers. Oh, why did I write primary here? This should be prime, I should say. So prime. Okay, so with that, guys, looking at the calculator to your left, so 5 divided by 10 once again, and from that, we have 50% chance. So 0.5. So what about for an odd prime number? So for an odd prime number, so meaning that we will be getting the intersection of both odd and then prime number. So meaning, guys, so if this is the odd number and this is for the prime number, we would now be counting everything that is in between. So with that, guys, this is 1, 2, 3, and 4. So from that, this is actually 4 divided by 10, or this is 0.4. Or by looking at the camera, that is 4 divided by 10. So once again, that is 0.4. So what about for an even prime number? Okay, so for an even prime number, how many do we have here? So since an even number, as you know, an even number is not a prime number, meaning that we will only count here. So whatever is left here. So from that, since we only have one number, this is equal to 1 over 10, or we have a 10% chance of having an even prime number. Okay, so for letter E, so we would now be solving for an odd number or a primary number. So, an odd number or a prime number. So with that, guys, what we would be doing is that we will be getting the probability of the combination of odd or A in unity with B. Okay, so for the third one here, an odd prime number, so that is now equal to, so this is now the probability of the intersection of A and then B. Okay, so what if we would be resolving this problem, however, the only given here are these ones here. So suppose that we are only given this data, and let's say that we are now to solve for letter E. When we say letter E, we are now solving for P, or the probability of the union between A and B. So how can we solve for this value without even knowing our Venn diagram or whatever is being asked here? So suppose that we only know these values. Okay, so what we would be doing here is just that we will just be adding the probabilities of A and B. So from that, guys, the probability of the unions between A and B is now equal to the probability of A plus the probability of B. Okay, so by looking at these values here, so we have 0.5 and 0.5. If you would be adding them, that is equal to 1. However, in our answer in the previous slide, our answer should be 0.6. So how come? Okay, so what happened here was that when we have solved for the probability of A, so if you can remember, when we have solved for the probability of A, what we did was just that we have counted all of the elements of A, and then we have just divided it by 10. Okay, so once again, that is probability of A. But when we have solved for the probability of B, what we did here was that we have counted all of the elements or all of the events in situation B or in set B. And if you can notice that we have used these 4 elements here twice, meaning that we have solved for, we have used for this we have used these elements in solving for probability of A, and we have also solved these elements, or we have used these elements in solving for probability for B. So with that being said, guys, this area here is actually redundant since we have solved for it twice. And in order for us to reduce or to avoid redundancy, we would now be subtracting the probability of this 4 or the probability of the intersection itself. So with that, that is now subtracted by or minus the probability of A in intersection with B. Okay, so with this, guys, substituting known values, this is now equal to 0.5 plus 0.5. So 0.5, 0.5 minus the intersection, which is 0.4. And with that, our answer is now equal to 0.6 as confirmed in our previous number. So they are actually the same. Okay, so what if, for example, that your Venn diagram would now look like this, whereas you do not have, you do not have the intersection of A and B. If that is the case, guys, then your what you call this, your probability or the probability of A and in unity with B is now equal to just the probability of A plus the probability of B. Since our value of the intersection of A and B will now be equal to 0. Okay, so take note, guys, that these two here, these two elements here are mutually exclusive, meaning that they do not have anything in common. Okay, so once again, mutually exclusive sets are sets that does not have anything in common. So if you would now be looking at this Venn diagram here, since they did not intersect, meaning that they are mutually exclusive. Okay, so we also have another term which we call exhaustive sets. When we say exhaustive sets, these are sets whereas if you would be getting the unions of these sets, it is basically equal to the whole sample space. So looking at our example a while ago, so A and B are not exhaustive since if you would be combining the two of them, A and B, so this is now its answer. Their set or their union is not equal to the whole sample space because we still have yellow, we still have indigo, we still have violet. Okay, but A and B, so as you can see here, for A we have black, white, gray. For B we have red, green, blue, pink. They are mutually exclusive. Once again, sets A and set B are mutually exclusive because they do not have anything in common. So once again, for mutually exclusive sets, these are sets that does not have anything in common. I think this should be sets that do not have anything in common. Then for exhaustive sets, these are sets whereas their union will now be equal to the whole sample space. Okay. Okay, so recap. If you are to solve for the probability of the unity of two sets of events, this is now given by the equation the probability of one set of event plus the probability of the second set of events minus the probability of their intersections. Okay, so this is now our general formula for the probability of the unity of two sets of events. So in the event that, so no pun intended, so in the event that the two sets of events are mutually exclusive, meaning by mutually exclusive is that they have not intersected. So if there are no intersection, meaning that the probability of their unity is basically equal to the sum of their individual probabilities. Since of course, this value is now equal to 0. Since once again, they did not intersect. Okay, suppose that we will now add another, let's say, set of events here, set of events here. So apologies for what you have seen. So suppose that this is A, this is B, this is C, and this is D, and all of them are mutually exclusive. So from that, in order for you to solve for their or the probability of their unions, just add their individual events. So there. Okay, so what about, let's say, if we would now be having three sets of events? So in order for us to solve for the probability of their union, this is now given by the equation. So the sum of their individual probabilities minus this intersection here. So that is now the probability of the intersection of A and B minus this intersection here. So P A intersection C minus this intersection here. But take note that we should now add. So again, we would now be adding this particular intersection at the middle, since we have already subtracted it 3 times. So from that, guys, this is now equal to plus the probability of the intersection of all of them. Okay, so this is now our general formula.